Tomorrow's Friday. But that's not why I'm not going to be here. Early. Slash recovery. Implicit differentiation is kind of a weird topic, but very understandable once you really kind of consider the why and not just the how. The explicit form of a function is when you have an equation that's solved for one variable simply in terms of the other. So it could be solved for y in terms of x, or x in terms of y, or p in terms of q. It doesn't matter, but solve for one in terms only of the other. All right. So it's not defined using the word in its own definition, basically. All right. So we have the explicit form, and then we have the implied form of the function. Right? So basically what this is telling us is that there is a relationship, an implied relationship between x and y, but it's not flat out telling us what that relationship is. We have to somehow figure that out. And when we talk about an explicit form, we're talking about something that lends itself to being graphed or part of a substitution or something along those lines. All right? So the implied form or the implicit form is the one where it doesn't explicitly state what y is in terms of x or x is in terms of y. All right. We generally know how to find the derivatives of explicit forms. I mean, there's some things that we still need to look at, like inverse trig functions, hyperbolic trig function. Basically, lots of names that you may not have heard of before. So, all the functions that you've heard of, we know how to take the derivative of those things. All right. It's the ones that you may not have heard of. That's what we got to work towards. All right, so that's kind of good news, because what it means is that we're slowly moving away from where pre-calc is going to be the thing to hold you back. Because in the early goings of any calculus course, when people, if they struggle, it's because of the pre-calc content. Then later on, it's no longer because of that, it's because of the calculus content, but that's not going to be the case here, because you're all working hard, doing the right thing, all that good stuff, motivational speech. You're very inspired right now. So anyway, implicit differentiation has a technique, but the technique doesn't necessarily tell you why you're doing what you're doing, right? The issue here is, and we could do a sketch and everything, but I just want to talk about it for a minute. When we have a function of y in terms of x, or even in an implicit form, x times y equals whatever, we tend to think that x and y are numbers in and of themselves, but we learned in the basketball project that they may not be. X and y may not be numbers, they may be other functions. All right, so when I go to take the derivative of some function y, if I know it's definitely a number, then I could treat it as a constant maybe. And if that's the case, if y is constant, then its derivative would go to 0. But if y is some kind of function that's an unknown function, then I would have to take the derivative of it as is. So let me take that y equals 1 over x for a second here and show you what we've been really doing this whole time. So first off, I'm going to rewrite it. So y equals x to the negative first power. But I'm going to write that y as y to the first power. All right. Now, when I take the derivative of this, and this is the part that makes it kind of weird. On the right-hand side, you don't need any explanation for that, right? You've been doing that enough. You would say that it's negative x to the negative second by the power rule. And then on the right-hand side, the left-hand side, you would say dy dx. And then I'd say, why would you use dy dx? And then you would say, well, because that's what you told us to use when we want to write the derivative of y in terms of x. Because dy dx stands for the derivative of y, and somehow the d on the bottom stands for in terms of x. Although it really doesn't, that's the way we say it. Otherwise, we have to say the instantaneous change in y per single unit of instantaneous change in x. That's probably too many syllables. All right, but here's what we've been doing. we have some unknown function y and some unknown function x, thinking in terms of the basketball project. Maybe y is equal to VO sine theta t minus 1/2 gt squared plus HO. And x is equal to VO cosine theta t. All right? So it's some function, it's not necessarily a number. So I'm looking at that y to the first power and I'm saying, okay, I got something to the first power. All right? So what I'm going to do is I'm going to apply the power rule. I'm going to say, all right, the derivative of that by the power rule followed by a little bit of chain rule action would be 1y to the 0th power times the derivative of whatever is in on the inside, the instantaneous change in y per instantaneous change in x. All right? That's what has been happening on the left-hand side. I just couldn't do it that way in the beginning because, what was it, like a week and a half, 2 weeks ago that we learned about chain rule? But we started talking about derivatives in October, like early October. So we had been using this notation, but this is where it came from. It came from the chain rule. So I couldn't wait to teach a chain rule without teaching you the notation, so it had to happen. Now, on the right-hand side, I have x to the negative first power, all right? But x could be some other function. So something to the negative first power. So following the chain rule, it would be -1 times whatever that something is to the negative second power. And so what I would be looking for now is the derivative of this something. Because it could be with respect to x, it could be with respect to a different variable, a lot of different possibilities, all right? If we're just assuming that we're taking the derivative in terms of x, then what I'm looking for is the instantaneous rate of change of my function x per instantaneous change in x, all right? Because these are going to be consistent. That's the variable in which I'm taking the derivative. I'm looking to find the rate of change in this function per unit of x. So that explains the denominator. The numerator comes from whatever variable you're looking to find the instantaneous rate of change of. All right. So all of that, once you clean it up, becomes dy dx equals negative x to the negative second. Because pretty much everything else cancels away. Dx dx goes to 1, y to the 0th goes to 1. So then what did we do? We just said, okay, well, y has a derivative of dy dx, just because. And x to the negative first has a derivative of negative x to the negative second because of the power rule, right? Which we discovered, but still. But this is really what's happening behind the scenes, because it allows for y to be some function of x and x to be some function of x. All right? It's very weird to think of it that way, but that's how it actually works. All right? And it also seems like I'm probably trying to make this unnecessarily complicated, but the reality is this little bit of understanding is absolutely necessary in order to find the derivative of a function in implicit form. Because you look at x times y equals 1, you say, okay, I can ignore everything you're about to say about implicit differentiation because I could just solve that for y and do what you did over here. This one you could also solve for y, but it's not going to look as nice. There's going to be some situations you just flip to the next page and you can take a look. Right? Try solving that for y in terms of x. All right? So definitely worth exploring. All right, the idea is that we always want to have in mind, and we'll do the sketch in a minute because the sketch is going to be easy. We always want to have it in mind that x can be a function, y can be a function, and we're treating it like chain rule. All right, so everything is a something now. So it's never just x to the second power or t to the second power. It's something to whatever power. So I'm looking at this guy right here. I'm finding the derivative using chain rule. It's something to the second power. So 2 times that something to the first power. that something is x, it has a derivative of dx dx. All right, seems like a wasted / unnecessary step, but we're building towards something, so you'll see. All right, the y squared. That's again something to the y to the second power. So the derivative of that would be 2 times whatever that something is to the first. That something is a y, and it has a derivative of dy dx. The right-hand side, I mean, you talk about somethings all you want, but derivative of a constant is what? 0. It doesn't matter what I'm taking the derivative in terms of x, y, smiley faces. It's a constant. Its rate of change is equal to 0. All right. Now, what I needed, and this is what I did, or the technique I used when I was a student, is because when we clean this up, any derivative involving an x ends up being the way it always was. So we have just a 2x, right? Any derivative involving a y has a dy dx slapped on at the end of it. So at least in the early goings, that's how I remembered it. I didn't understand why. I don't think I was paying attention either. But, or I was absent one of those weeks. I was absent a lot, like first half of high school, pretty much there. After that, got a car, had like 3 periods off in the middle of the day. So I was like, all right, 4, 5, and 6, I'm off. There's like 5 minutes left in 6th period, and I'm like 15 miles away from school. I'm like, all right, I'm gonna take a loss on this day. So a lot of days ended early for me. I'm not a good example of proper senior year behavior. So anyway, I try not to be too much of a concern about that. But anyway, so yeah, I'm sure it was a riveting explanation by Mr. Duncan. I mean, it was, Miss P hated him, I loved him. But that it's, you know, different strokes for different folks. But yeah, he had great explanations for me. I think I might have missed this one though, because I had no idea why I was doing it. I just knew that anytime I took a derivative involving an x, it was the way it always was. Anytime it involved a y, I just slapped on a dy dx at the end. And then later on, I would get stuff right. Later on, it slowly started to dawn upon me, or some glorious divine intervention. I don't know. I don't know what happened, but I actually started to understand it. And then after that, I became a math teacher in history. But and the world was changed forever. So, yeah, I mean, at this point, that might be what you do. All right, it's not solved for y. So anytime I take a derivative of a y term, just slap a dy dx on at the end. And then later on, it'll be like, oh, that's why. And it'll be weird, because you'll be sitting in the cafeteria eating like a couple of French fries. Do they allow you to eat French fries in this district?
We don't have French fries.
No, it's not available, right?
They had them for like a week, and then we all complained.
Yeah,
They were soggy and gross.
yeah, they're like wheat fries now or something like that. Oh, tater tots? Do they actually have potatoes in them?
Yeah.
They're not bad? Okay, all right, yeah, because you never know. I mean, like, no more meatballs, wheat balls. That's what we have there. I had those once at Mr. Nidell's wedding, and he's like, they taste just like meatballs, don't they? I was like, yeah, they totally. I mean, you put enough sauce on something, you can pretend it tastes like anything. So at one point, it became just like sauce with like floating bits of mush in it, but it was, I mean, edible at that point. So yeah, anyway, you'll have that moment, that aha moment. You'll be mid tater tot, and you'll be like, oh, and then everybody will look at you and you'll be like, whoa, what just happened? And you'll be so embarrassed. You'll be like, I'm not admitting this. You'll be like, no, I just burned my tongue, dude. Like, it was a very hot tater tot. You're not going to admit that you actually grasped something that had been eluding you for a while. That happened to a student in the middle of a library with a Ken puzzle. He was working on a 6x6. It was like March, and he'd been trying them religiously every day for the entire school year. Gets to March, finally gets one. Checks it. He's like, yeah, baby! And then realized where he was. And then he did the only thing that he could think to do at that point. It's like, I just got into college. Because he needed to justify his reaction with something. And it could not have been a 6x6 Ken. It was the funniest moment ever. So. Yeah. Be like, check this out. Check out this little square rectangular piece of paper, whatever. Square rectangular. I'm on fire today with nonsense.
Mr. Ken, were you in the library?
That day, yes.
Were you like, shh?
I was like, all right, that is it. Oh, Ken. All right. Nah, actually, I wasn't in the library. He told me about it.
Do you remember the time you kicked me out of the library?
You know what? I gotta tell you.
Will was there too.
I have
when we got kicked out of the library.
so many people out of the library that your faces all blend together.
It was like blushing, right?
Yeah. We were
Wait,
there
who
for like 5
knew?
minutes.
It was me, Brianna, Cameron Shapiro, and Daisy O'Neill. I think we were at a table together.
Yeah.
Oh, so I have 3 out of 4 of you this year. That's great.
Yeah.
I should take that like every other day, but I seem to rebel it.
I got Reed once.
Johnny's not here.
Yeah, I think he was freshman, sophomore.
Oh.
Yeah.
That was a freshman.
Nah,
Cry.
yeah. Yeah, it had to be. I mean, it's always tough. It's always.
Wait, Mr. Ken, what periods are you in the library? I need to get kicked out.
This year, not at all.
Not at all.
But you know
I
what?
kicked out, but I don't want the teacher to hate me.
I was eating in the library, and the librarian came and she's like, don't eat. And I was like, okay. And I just stuffed it.
The issue with me with the library is the concentration component. Like, when I'm grading papers, if I'm reading the same line, I'll look down and be like, I am on the same paper. And it's been 15 minutes. The same question on the same paper, because every time I'm like, okay, so this is right, that's right, that's right. Shh. All right, where was I? Crap, I lost my train of thought. All right. So, a little tick up in the aggravation department. And then, like, 20 minutes later, it's all over, you know? And then I finally get it quiet. And then your sister comes walking in and be like, hey, Mr. Garrett, how are you? What's going on? I'm like, oh, God, I got him. Kid, I just got him quiet. So, or another teacher, which is a student I can deal with. The teacher is what gets me. But then how do you tell Mr. Smith to shh, you know? It's like, I'm like ready to be like, oh, it's Mr. Smith. So.
My friends do the good old, I love you, but can you stop?
Yeah.
No, I don't understand.
So we'll find out tomorrow. Well, actually, I won't because I won't be here, but we'll see if you watch the video. Should I tag him in it? So anyway, negative x over y. If I solve for dy dx, because that's the goal here, to get dy dx alone, which would be the derivative of y in terms of x. There are some situations where you might want to solve for dx dy, the change in x per unit of change in y, but they flat out told us to find dy dx, so you go with what they asked me to do. So I subtracted the x divided by the y. This is not at all remotely like what the derivative would look like if I solved this function for y and then took the derivative of that using chain rule. But, yeah, I mean, you could try it. I think this ends up being, once you get the hang of it, a nicer approach. It's definitely simpler in terms of the calculations that you do. It's power rule all the way. As opposed to solving for y, getting a plus or minus in there, which is always fun, then chain rule, and then cleaning it up. I'm not interested in that. All right, now in terms of the function itself, well, it's not a function, that's the key, I guess. What kind of equation is that?
It's a circle.
It's a circle. I can't draw lines for some reason. Center where?
I know. Like,
At the origin, radius? 4. All right, so that is, that's a beautiful circle. I mean,
Perfect circle.
it's like I use a compass.
Remember when Miss Maggie Nelly was
All right,
she would make like an over.
so all the points where the graph has a horizontal tangent. Well, I don't need my derivative to figure that out. It's got one here. That would be a horizontal tangent.
It's a decent circle. It's not second.
And that would be a horizontal tangent. All right, so the points where it has a horizontal tangent, well, in terms of x, that would be at x equals 0. Now in terms of y, I'm sorry, in terms of x, where it has a vertical tangent, you'd be looking at 4 or negative 4. All right, you could also state the y values if you wanted to. All right, so the y values would be 0. But you could get that by solving this equation. Horizontal tangent you get by setting your derivative equals 0. You get x equals 0 if you do that. Vertical tangent you get by setting your derivative equal to 1 over 0. So you would do something like 1 over 0 equals negative x over y. And you get y equals 0, which corresponds, when you plug it back into the original function, to x squared plus y squared equals 16. All right.